Mr. Tarrou, in this lesson we're going to be taking a look at graphing three examples of absolute value functions as piecewise functions. When you go into calculus, this may very well be an Algebra 2 honors course or pre-calculus course. When you step into calculus, it's going to be important that we understand there is a relationship between piecewise functions and absolute value functions. And so when you go to find a derivative or integrate functions that involve absolute values, they're easiest if you rewrite them first into piecewise functions. So we're going to look at that relationship today through graphing. And piecewise functions also have a lot of applications in the real world. It might be something to do related to your cell phone bill. If you look up how we pay our federal income taxes, that's based on a big old piecewise function. So they have a lot of applications. We're going to set the expression inside the absolute value function equal to 0. That's where those absolute, maybe you remember from maybe your Algebra 2 lessons, something like simple like this first example, y is equal to the absolute value of x plus 3. With this being a linear function inside of our absolute value function that has an exponent or degree of 1, this is just going to be like a V shape. And that sharp bend is going to occur, at the value of x that makes this expression equal to 0. And by the way, you might be looking at this going, I already know how to maybe graph this, understanding what the parent function looks like, y equals the absolute value of x, and of some understanding of transformations. This is just going to be a shift to the left 3 places. But of course, we're going to step up the difficulty a little bit as we go through our 3 examples, and you will see the power of rewriting these as piecewise functions as we go along. Timestamps to those 3 examples are going to be in the description as well. We're going to use a solution that we get from step 1 to set up our piecewise function. Now, it's like the solutions from step 1 are almost critical values that are along your number line, and that those critical values, between each of these critical values or solutions from step 1, we're going to have intervals along the number line. And if you have a interval, you're going to test one point, and if one point or numerical value within an interval creates a final, after you simplify, creates a solution which is negative, then we're going to rewrite the function but replace the absolute values with a set of negative parentheses, because of course we like to say that absolute value symbols just sort of gets rid of a negative sign, but really it tells you how far a number is away from 0 on the number line. And so if you look for the absolute value of -5, it's going to change the sign apparently and give you an answer of +5, because -5 is 5 steps away from 0 on the number line. Whereas if you take a look at the rest of this, it says replace, or where the expression is positive, we're going to just simply drop the absolute value. If you take the absolute value of +3, that's 1, 2, 3 steps away from 0 on the number line, so the absolute value of 3 is just 3. The absolute value function doesn't really seem to be doing anything. So for that interval, we can just drop the absolute value function notation. And then we're going to graph our piecewise function. And if you have in the past struggled with graphing these piecewise functions, I'm going to hopefully help you understand how to do that, of course. First example here, we have y is equal to the absolute value of x plus 3. And again, we're not going to be graphing this using our knowledge of transformations. We're going through these steps with an easy problem so we can see how it works and move into the more complicated ones. Step 1, we're going to take the expression that is inside this absolute value function. Well, that's x plus 3. Set it equal to 0, solve that. So we're going to subtract both sides by 3. So -3 is sort of a critical value, if you will. It is the x-coordinate or x value that where we're going to have a sharp bend in our graph. And let's see, how about we put a number line down here? We have 0, 1, -1, -2, -3. And again, this -3 is going to now break up our number line into two intervals. We're going to look at these intervals and think about, well, what if we try -4 or -5 or any number that's to the left of -3 on the number line? Well, -4 plus 3 is -1, and the absolute value of -1 is +1. So when we set up this piecewise function, we're going to need to replace the absolute value function with a set of negative parentheses for any value of x which is less than negative 3. And then to the right of negative 3, like maybe 0, well, 0 plus 3 is positive 3, and the absolute value of 3 is just 3. The absolute value symbol is still telling you how far away from 0 you are on the number line. But as far as the sign's concerned, it kind of just seems like it's not doing anything. So for x is greater than or equal to negative 3, we're just going to drop those absolute value symbols, and this is what it's going to look like. Y is going to be equal to, and I'm going to use these kind of curly brackets here because our piecewise function is going to be into two parts because we've only got one solution from setting the expression inside the absolute value function equal to 0. One solution gives us two intervals. So we have replacing the absolute value with a set of negative parentheses. We get negative parentheses x minus 3, and that's going to be the equation we use, again, for when x is less than negative 3. Now, if we use values of x, if we're to the right of this critical value, if x is greater than or equal to negative 3, well, like when I said, when I tried 0, the absolute value of 3 is 3. Nothing really happens, so we can just rewrite this equation, but with no absolute value notation and no sort of negative parentheses because we're not really changing any signs. Rewriting this a little bit, we can distribute the negative 1 through these parentheses, and we get y is equal to, well, negative x plus 3 for when x is less than negative 3, and x, I was thinking ahead of already changing these signs, so that should be x minus 3. Glad I caught that mistake. That would be a little bit awkward later. X plus 3 for when x is greater than or equal to negative 3. Okay, so now we've got our piecewise function set up. We basically are just going to graph two lines. Y is equal to negative x minus 3. We'll do that, say, in purple. I hope that's going to show up. And we've got, in blue, y is equal to x plus 3. And I have students all the time that struggle. Oh, I can't use blue. I've got my blue x and y axis. How about we do that in orange? I have students all the time that struggle with graphing piecewise functions, but I have to remind them, and sometimes usually it works, and sometimes we need to remind this ourselves a couple of times, but we're just graphing a couple of equations on the same xy axis, and y equals negative x minus 3 is nothing more than a line. We have a y-intercept of negative 3, and I said that was going to be in purple, so y equals negative 3 is right here. That's a y-intercept. Our slope is negative 1, so down 1 over 1, and over and over and over again. Now I'm re-emphasizing here that when you graph piecewise functions, you're just graphing a couple of equations, or maybe 3, well, it could be more as well, but you're graphing multiple equations on the same xy axis. So I know there's a condition here, but we're just graphing y equals negative x minus 3. And now in orange, we're going to graph y is equal to x plus 3. Well, this is a slope of 1 and a y-intercept of 3. So 1, 2, 3 on our y-axis, up 1 over 1, up 1 over 1, so on and so on. And I just graphed two lines. But this condition, x is less than negative 3, is for this equation y is equal to negative x minus 3. So this first graph I drew is not supposed to appear anywhere except where x is less than negative 3, or to the left of negative 3. Well, there's negative 3 right there. And when I look here, x is negative 2, negative 1, 0, 1, 2, so on and so on. All of these x values are not less than 3, they're greater than 3. So we're going to take this out. Again, just in case you're having trouble graphing piecewise functions. And this inequality does not have an equal sign. So actually, this purple line, y-intercept of negative 3, slope of negative 1, should have an open dot here at x equals negative 3. But now we come along and go, well, wait a minute. We also graphed y is equal to 1x plus 3, and that yellow or orange line is supposed to be everywhere that x is equal to negative 3. Well, equal to means that I can come in here and fill in this hole from the purple line, And they don't always necessarily line up. But then x is greater than negative 3. X is to the right. All the x's to the right of negative 3 are going to be within or representing, or we're using this second part of the piecewise function for those values to the right of negative 3. Well, here I'm to the left, negative 4, negative 5. Those aren't bigger than negative 3. They're less than negative 3. And here is our graph for y is equal to the absolute value of x plus 3. A little bit different than when you were, maybe seeing this as a transformation, the parent function y equals the absolute value of x, and just shifting it to the left 3 places. This is actually a longer technique, but you'll see in our next 2 examples that this going into a piecewise function idea makes things actually simpler. And if you need a little reminder of domain and range, of course, when you identify the domain of a function from a graph, that's about all the values of x that are included. And as you move left and right, where's the graph? Well, the graph is everywhere. So all of these values of x, all these values along the x-axis are part of the domain. Now the range, I think my wife picked up the phone there. Well, the range is about the vertical motion, or the y-coordinates values that are included in your graph. Well, the lowest this graph goes, it goes down to the x-axis. So the smallest y value that this graph includes is a y value of negative 1, and that is a solid dot. So we are including the lowest y value of 0 and then going up to infinity and beyond. Now, for our second example, right now. Alrighty then, so for our second example, we have y is equal to x squared plus x minus 2 over the absolute value of x minus 1. Looks like it's going to be a lot more complicated than our previous example. But if you think back when we were, hopefully you've covered it already, graphing rational functions, we talked about finding holes and vertical asymptotes when graphing rational functions. Now this is not just any old generic rational function. We have an absolute value sign down here, but the numerator, we talked about if you could factor the numerator and denominator and have a factor which would cancel, then that factor in the denominator, the x value that makes that factor equal to 0, there would be a hole in the graph there. Now, if there was a value of x that allowed the denominator to be equal to 0 and it did not excuse me, cancel or divide out with something in the numerator, well, then you have a vertical asymptote. So we talked about, okay, factor in the denominator can possibly equal 0, vertical asymptote unless it can cancel with a common factor in the numerator, and then therefore at that place you have a hole. And that's for rational functions. Things get a little more complicated if you have like trig functions and such, but for rational functions, that's the way it worked. Well, if you keep that in the back of your mind and you go, well, this quadratic has a leading coefficient of 1, so we're only looking for, if we can factor this, factors of negative 2 that add to the middle coefficient of positive 1. Well, and negative 2 is prime, so it's either going to be 1 times negative 2 or negative 2 times 1. Well, yeah, negative 2 times 1, when you add them, like when you're distributing to create that middle term, adds up to be positive 1. So this is a factorable quadratic. And I will put links in the description for graphing rational functions if you want that review, graphing absolute value functions using transformations. If you need a review of factoring, I'll put a link to my playlist in the description as well. But we're going to have y is equal to x, okay, factors of negative 2 that also add to be positive 1, okay, because its leading coefficient is just 1. So we got x plus 2 and x minus 1 all over our denominator of the absolute value, not just x minus 1. This isn't going to straight away yet cancel, but we have the absolute value of x minus 1. Well, again, talking about graphing rational functions, if we can get this x minus 1 to cancel out, we can get what looked like a really complicated problem, and it might just end up graphing very similar to a line or pieces of lines, but we do have to deal with this absolute value sign. And by the way, we do have a fraction or a division in our problem, and of course we cannot divide by 0. So as far as the domain of this function goes, the denominator, the expression in the denominator, x minus 1, cannot be equal to 0, thus x cannot be equal to 1. So we're going to be, kind of two parts. The original set of directions said, hey, if you got an absolute value in your function that you're trying to graph, let's make it a piecewise function. Let's take the expression that's inside the absolute value function, set it equal to 0, and solve it. That's where the sharp bend is going to be. At least if it's sort of like those simpler style of problems we did when we first started looking at graphing absolute value functions. Well, here, the x minus 1 is inside the absolute value function, so good. We have some kind of critical value we'll use for setting up our number line and our piecewise function. But we're also restricting the domain. X will never be 1, otherwise you're dividing by 0, and this is undefined. Even if it cancels out and simplifies to a simpler looking equation, the x minus 1 is still in that original denominator. So, 0, 1, 2. There's the 1. There's the critical value. If you plug in 0, you have 0 minus 1, which is negative. So for x values that are less than 1, we're going to have to replace the set of absolute values with a negative parentheses. Now, when you go to the right of 1 and you say maybe check 2, 2 minus 1 is 1, the absolute value of 1 is just 1, nothing seems to happen. So when x is greater than 1, we can just drop the absolute value symbols altogether. Do a little bit of canceling of our common factors now. Anything divided by itself is equal to not 0, but negative 1. So we're left with a negative 1 in the denominator. And I'm going to, when I rewrite this, let this negative 1, when you divide by negative 1, like 5 divided by negative 1 is negative 5, and negative 1 times 5 is negative 5. So I'm going to let this negative 1 kind of seemingly float up in the denominator. I actually don't even like to say that, because sometimes my kids will have some like 0 over 5, and they let the fly float up and say it's 5 instead of 0 and all kinds of crazy things. But I'm going to distribute that negative 1 through the parentheses. And here we've got the x minus 1 divided by x minus 1 is, of course, again, coming out to be positive 1. Even when I'm not talking, sometimes I'll make some kind of silly mistake like that. But at any rate, x minus 1 divided by x minus 1 is negative 1, and x divided by negative 1, that's a nice way of saying it, is negative x, and 2 divided by negative 1 is negative 2. We have our y is equal to x plus 2. And we're done setting up our piecewise function. You might also remember from solving absolute value functions that we would isolate these absolute value functions and then rewrite that problem into two separate equations, one with no absolute value sign and one with a set of negative parentheses to finish that solving process. So it's not the first time we've taken absolute value functions and rewritten it as two separate functions. Okay, so like the previous problem, we are again graphing just simply two lines together on the same xy axis. We're going to be graphing y is equal to negative x, so there's a slope of negative 1, minus 2, y-intercept of negative 2. And it's only going to sort of show up, we're only using this particular equation for x values which are less than 1. So here is our 1, and we have a y-intercept of negative 2. Our slope is negative 1, so down 1 over 1. Now I'm not going to put, I want to kind of just draw this and not erase it as we go, or after I'm sort of partially finished. X has to be less than 1, not equal to. So we're not going to put a closed dot there, we're going to put an open dot. And then kind of going in the opposite direction, instead of down 1 over 1, we're going to go up 1 over 1, and so on, and so on. And we have this. And that's the first part of our piecewise function. Now moving on to the second part, we're graphing y is equal to 1x plus 2, so a slope of positive 1, and a y-intercept of 2. Yes, I kind of just glanced and wasn't sure, making sure I did that right. This part of the piecewise function only works, or only comes in for the condition where x is greater than 1. So again, no equal sign here, so we're going to start with an open dot. Our y-intercept is 2. and from there we're going to go up 1 over 1. So we're starting at 2. I'm not going to make a dot there because I'm to the left, not to the right of 1. I'm going to go up 1 over 1. I'm at x equals 1. I'm not including x equals 1, no equal sign, so an open dot. Don't just skip all the way up over here to 2, because 1.00001 works. It's part of this domain, if you will. We're not graphing integers, okay? So we're not going to jump over here to x equals 2 or x equals 3. And up 1 over 1, up 1 over 1, so on and so on. And this is the final version of our graph. Now the domain, just in case, I used to never talk about domain and range with every graph I made, but as I've made more of these YouTube videos and I hear people's questions, that's a common one that gets asked. As you look across this x-axis, the graph's there, the graph is everywhere except when x is equal to 1. You skip over just 1. You're right up to 0.9999 and you're right next, right on the other side, 1.000001. That's not exactly equal to 1, so it's part of the domain, and you go off forever to the right. So the domain, I'm going to write this in interval notation. We can say the domain is all real numbers except x cannot be 1, but my textbook uses a lot of interval notation, so we're going from negative infinity to 1, or from 1 to infinity, those round parentheses indicating that I'm not including the value of 1, I'm just approaching it from basically the left and the right. The range, well, what's the smallest y value that's included in this graph? I got y values of whatever these are, 3, 6, 7, 8, 7, 6, 5, everything in the middle, all these decimals, all the way down until you get to a y value of, I think I might have said x before, but a y value of 3. And it's not included, but no. There's a graph over here. The graph in its entirety does include the y value of 3. It's just over here instead of over here. And we go down to the lowest y value of negative 3, but it's an open dot, not closed. So our lowest y value is approaching the y value of negative 3. So around parentheses, because we're not really including it, open dot, not closed, negative 3 to infinity. And beyond. And on to our third and last example. No. So for our last example, we have y is equal to the absolute value of x squared minus 4x minus 5. This time, the function inside the absolute value is not a linear function. So this isn't going to be just a simple v, or like you saw in the previous example, a couple of line segments. But we're going to do the same thing as we did before. We're going to recognize that this is going to have some sharp bends. We're going to use that inside function and set it equal to 0 to find out where those sharp bends are. Find out what critical values, where the breaks are going to be in our piecewise function. This is, again, a quadratic with a leading coefficient of 1, so it's not as bad as it could get for factoring, and 5 is also prime here. So we've got factors of negative 5 that add to negative 4, that's negative 5 and 1. So we have x minus 5 times x plus 1 equals 0. Setting these equal to 0 and solving. Good. So our sharp bends are sort of interesting points, if you would. We actually did not have sharp bends in the last example. It was just a couple of disconnected line segments. But the interesting stuff is happening at negative 1 and positive 5. So looking at the three intervals along the number line, which are created by these two solutions, think about the value of, let's say, negative 2. Negative 2 minus 5 is negative, and then negative 2 plus 1 is negative, and negative times negative is positive. So this expression, either in factored form or the original quadratic, is going to be positive for values of x which are less than negative 1. Now if you think about something in the middle, like between negative 1 and 5 you have 0. Well, if you look at testing an x value of 0, 0 minus 5 is negative. I know it's negative 5, but we're really just keying on the sign, whether this is given a positive or negative answer, so we know what the absolute value functions have to do. Negative times, well, 0 plus 1 is positive, so negative 5 times positive 1, or just a negative times a positive, comes out to be a negative answer. So for the x values between negative 5 and 1, we're going to have to replace this parentheses with a set of opposite let's try that again. For x values of -1 to 5, we're going to replace this absolute value function with a set of negative parentheses. Now to the other side of 5, we have, well, let's say 6. 6 minus 5 is 1, or positive. 6 plus 1 is also positive. So testing that 6, we have a positive times a positive. So for x values to the right or greater than 5, we're just going to drop these absolute value signs in, just as if they weren't there. So now that we have these intervals set up, we're going to write out our piecewise function. Okay. Just going nice and slow, making sure that I have that right. So when x is less than or equal to -1, I'm including the equal signs in the first and third line because if the absolute value of 0 is 0, just a small technicality, but we don't need to introduce negative parentheses for when this expression is equal to 0, just when it's less than 0. So we had between -1 and 5 needing to replace these absolute value signs with that set of negative parentheses. Now, we are just talking about doing a sketch. Busy night for the phone. Okay, my wife got it. We are just kind of talking about sketching, not doing a lot of points and making a super accurate graph. We certainly could, I guess. But in terms of just sketching, you might recognize, if you're talking about graphing absolute value functions and stuff, I'm sure you've talked about graphing polynomials. We have a quadratic, a second degree polynomial. Polynomial just means you have one variable and all your exponents are positive integers. We're just graphing a parabola that is opening up. And this parabola opening up, not only are these sort of critical values we're using to set up our piecewise functions, but they're also, look, y is equal to 0. They're also x-intercepts. So this opening positive leading coefficient parabola, degree of 2, has x-intercepts of -1 and 1, 2, 3, 4, 5. And when you are, to the left of -1 or to the right of +5, it's kind of like opening up as you would expect. And again, this is just a sketch. Maybe I'm not really sure where the parabola is going to be when x is 6 or when x is -2. We could plug them in, of course, but just as a sketch. And then the graph is coming through, and wait a minute, this parabola now has a negative, replacing that absolute value sign with a set of negative parentheses. Well, think about it. You plug in an x, you multiply it by 4, you square it, you do a little bit of addition, subtraction, you get like an answer for y, but then nope, you change the sign. So instead of all of these negative y values, all the absolute value sign is going to do is make all those y values positive. So instead of the graph coming through here and then just falling below the x-axis, between -1 and +5, the absolute value sign is going to turn all those y's that are negative into positive. So the graph is going to kind of just sort of bounce off the x-axis. Now, I could say, you know what, let's just do this. How about, think about when x is 0, just so we get one more point in this graph. When x is 0, for a y-intercept, we have 0 minus 0 minus 5. So the y-intercept of this graph, actually, I have this not really the right shape. It would be intersecting the y-axis at 1, 2, 3, 4, -5. Well, with that reflection, or with the absolute value symbol having to be replaced with a set of negative parentheses for the values between -1 and 5, instead of intersecting at -5, it's going to intersect at +5. 1, 2, 3, 4, 5. And the graph is going to look, I have a feeling as sharp as that, it's going to go up quite high, but it's going to look something like this. Now, if you want a more accurate graph of what this parabola should look like, you have two ways of finding the vertex. One way is you can find, kind of thinking about this up here, but without the reflection, and just know that we're going to take the y value and make it positive. Now we're moving sort of beyond the old idea of graphing absolute value functions. We're doing a little review of quadratics. When you have x squared, y is equal to x squared minus 4x minus 5. In this format, you can do, well, the x of the vertex is equal to negative b over 2a. And now we've got negative, well, b is negative 4, so the opposite of negative 4 over 2 times a, well, that's our leading coefficient of 1, and 4 divided by 2 is 2. So the x of the vertex is equal to 2. Now if you want the y of the vertex, you just go back and figure out, sort of like, you know, if I was using function notation, I'd say figure out what f of 2 is, and plug 2 in here, find out what the y coordinate is, and then, you know, plot that. We got, well, we can do that. I guess we got 2 squared is 4. We've got negative 4 times 2 is negative 8. So we have 4 minus 8 is negative 4, minus 5 is negative 9. So actually, at the x value of 2, 1, 2, 3, 4, 5, 6, 7, 8, 9, instead of being at y equals negative 9, it's going to be at 1, 2, 3, 4, 5, 6, 7, 8. Oh, I could fit it up here at positive 9. Well, now we're making an even better version of our graph, and say that it looks like this. And then boom, bouncing off the x-axis, something to that effect. Now, another way that you can talk about graphing this parabola is by completing the square for this and getting it into what's called vertex form, or, well, it depends on the textbook you're using. It might call it standard form, might call it vertex form. I'll have a link to that as well if you want to review graphing quadratics by completing the square to put it into, again, that vertex or standard form, depends on what your textbook calls it. I'm Mr. True. Hope this all helped. Bam! Go do your homework.